And I'll get this set up from current slide. And I'll turn on the projector and go through the announcements. Sorry about my voice, but I went to the UAB game Saturday, so my wife says I should know better. I probably should. All right, today being September 23rd, our volleyball team has a match tomorrow evening. They're playing Coastal Alabama East. I guess they've combined so many, merged so many schools together. I guess they're what used to be another school and another school merged together. So now the one school is the East and the other school is the West. I don't know. But anyway, they're playing them tomorrow evening, 5 o'clock. It's a home match, so it's on the Birmingham West campus in the Arthur Shores Fine Arts Building, which is also the gymnasium. I find that interesting, Fine Arts and Gym. The Fine Arts is the very first few classrooms here, then the gym, the weight room, the swimming pool, everything else is there, but it's the Fine Arts Building because it has about 3 or 4 classrooms for Fine Arts. I guess, I don't know, it's rather bizarre. I guess they could get more money for a Fine Arts Building than they could for a gymnasium. So
kind of surprising in Alabama.
Yeah, I think that's it. Okay, the next match coming up will be Wednesday. I'll announce that when it's closer. On Wednesday. The College Scholars Bowl team is currently recruiting players with a knowledge of any subject whatsoever, including history, literature, science, music, current events, mythology, mathematics, and even if you're not a master of any of those, if you're a jack of all trades, they'll get that. I'm sorry, Bill, didn't know you were looking for a pencil sharpener. I had a high-tech one up here on my desk.
Well, that's what I'm looking for, those high-tech ones.
Oh, yes, okay.
They don't even know what this is, so.
All right. So, if you are interested in participating, Mr. West is the coach. His office is just down on the lower level of the second floor, and it's between 259 and 261. If you go down the half flight of stairs after the stairwell, the first classroom on the left is 259, then his office is 261. Good guy, good time, good team. Today is the last day for the Darkness into Life Alabama Holocaust Survivors through Photography and Art exhibit over on the Birmingham West Campus Library. That will be on display through today, September 23rd. Okay, last chance to see it. I got to just glimpse at it when I was passing by the library on Friday, but I was so far behind. I've had so much to do, I couldn't afford much time to come here. Oh! Get in there. Thank you.
I'll put this high-tech object back.
What's that?
I'll put this high-tech object back because
absolutely.
These are running out of.
I cherish that. They have one not quite so high-tech hanging on the wall in the copy room, and I've never seen a flimsier thing in my life. I mean, it looks like if you touch it, it's going to fall to pieces. But the NASA's Community College Aerospace Scholars Program is accepting applications for this year's activities through October the 16th. So between 2 and 3 weeks away. There's several websites you can go to for e-flyers, website, videos, and other things. So if you're interested, it's a great program. At least all the students I've taught with who participated, we've had several. They've really thoroughly enjoyed it. All right. Got y'all here. Any questions, anything we've done so far? All right. Now, where we left off last time, I believe we're in Chapter 12, Vector Value Functions, 12.4, Tangent Vectors and Normal Vectors. We've been hitting all over the tangent vectors. Last time toward the end, did the first of the principal unit normal vectors, and we're picking up on page 848, very top of the page was where we ended on the previous page, starting on this page today. The principal unit normal vector, what an understatement here, can be difficult to evaluate algebraically. As we saw in that last one, it is involved. For plane curves, you can simplify the algebra by finding first the unit tangent vector, and that's pretty easy to find, relatively easy. Write it as an x of t I y plus y of t j, observing that the unit normal vector must either be y of ti minus x of tj, or minus y of ti plus x of tj. Why? They're perpendicular, and the only way you can get these two nondescript functions here to be, their dot product to be 0 is x of t times y of t is plus xy, y of t times minus x of t minus xy, that would go to 0, or minus x, y plus xy equals 0. That's the way. So one of those two is going to be your principal unit normal vector. Which one? The one that opens to the inside of the curvature. Okay? They'll get to that next, but that's what's coming. Okay? Oops, I'll leave that. And that's just simply because of the unit tangent vector and the unit normal vector must be perpendicular. Yes?
Can we get lazy on that, and once we find the unit tangent vector, just change the signs and put the things
That's
together?
exactly. That's
We do
exactly what we do. Yeah, that's exactly what they'll say. Switch the two, change the sign of one. Now, which one do you change? That's the issue for the unit tangent vector, unit normal vector. Okay? But that's exactly what they do. If you got a two-dimensional planar situation, that's exactly what you do. 3 dimensions, you can't quite do that, because you got 3, and there will be basically an infinite way to get that dot product to be 0. Those are the only two. And that would have made our entire life a lot easier on the previous problem if they'd have told us this first. But you had to see for yourself how miserable getting that would be algebraically. Actually, I made it a lot more miserable than it needed to be. But that's my job, right? Never mind, I'm just kidding. Okay. So, now, if that unit tangent vector, remember, was x of t I plus y of g k, unit vector, that meant that x of t squared plus y of t squared, square root of that has to be 1 because it was a unit tangent vector. Well, if you just swap these two and negate 1, which is what we did, then x of t squared plus y of t squared is still 1, so both of these are unit normal vectors. The principal unit normal vector is the one that points toward the concave side of the curve. opening to the concave. Now, even if that curve looks a lot like a straight line here, find out where it was coming from, where it's going, and it always points to the inside. The one we did before, I don't know if you recall, I believe that's exactly the same. Yeah. When we did at value 1, the unit tangent vector was this. I don't know if we actually did that in the previous example. But that's what it was. And then this would be the one pointing to the inside toward a negative x, positive y, that's pointing this way. The other one would have been pointing this way, and that's obviously pointing to the convex side of that curve. I say obviously. It's not so obvious here until you see that the unit tangent vector, if they've drawn it properly, is a little on the outside, so it had to be on the inside. Down here it looks like it's part of it, but you see, you can't tell, is this now bending up somewhat? If it is, no, I'm sorry, if it is bending up, it could be, have already passed an inflection point and started bending down. Well, then this would have been on the inside, and it's not. But without that unit tangent vector there, you can't tell for sure, okay? Because that looks like almost a straight line. It's not a straight line, it's a function, but it's not entirely clear which way it is. Well, yeah, this lets you know it is a parabolic form. The curve is parabolic. So if you know where the curve is anywhere, you know where it is everywhere. So Pressel always points toward the concave side of the curve. Okay. This also holds for curves in space. That last sentence only, it always points to the inside, the concave side of a curve. That is for an object moving along a curve C. Here's the curve C. Okay. In space, the vector t as a function of t is tangential to that curve and points in the direction the object is moving, whereas the unit normal vector is orthogonal to the t, but it could have been to the outside or to the inside. The t is on the outside of that curve, the n is on the inside. If you'd have put the n over here, then they would have both been on the same side, and that's not going to be the case. Okay? Because n of t is orthogonal to t of t and points in the direction in which the object is turning. So the unit normal vector tells you which way it's turning. So it always is pulling you to the inside, pointing to the center of that curvature. Any point on the curve, the unit normal vector is orthogonal to the unit tangent vector for sure. The principal unit normal vector points in the direction to which the curve, in which the curve is turning. In other words, there is a circle, for instance, that matches that curvature right in that immediate vicinity, and this has to be pointing toward the center of that circle. They call it an osculating circle. This points to its center. All right. Looks like to me they're skipping example 4. So let's go back in time here to find a good place to do that. All right. Let me get my pen set up. All this yakking, I haven't even set up my pen yet. Okay. Finding the principal unit normal vector. Find the principal unit normal vector for the helix R of t. Boo hiss, this is not a planar situation. This is a three-dimensional. R of t is equal to 2 cosine ti plus 2 sine tj plus tk. some reason my screen is, I don't think it's doing it up there, but it is here. It's sort of fading in and out. It's not a good sign. I don't know what it means, but it can't be good. TK. I guess it's my writing on this wiggling it. That must be what's creating the disturbance. Okay. So it says find the principal unit normal vector. Now the good news is we've already done this one, or something very similar to it, and they're pointing us to this. This was the one we did last Wednesday before that last one, okay, when we found the tangent vector. So they're picking up from there so that we don't have to redo it. Do you want to redo it just for the memory of doing that? Or do you want to just pick it up from where we left off Wednesday? You want to re-see how to get the unit tangent vector? Okay. Well, they tell us, and this is the result of example 2 from last time, and this is not at the specific point, but it says find t of t, so this is the first part of the problem, and that unit tangent vector as a function of t, little t, doesn't have to be time, I usually say time, but it doesn't have to be, is 1/5, no, 1 over root 5, I can't read, 1 over root 5 times minus 2 sine t I plus 2 cosine t j plus k. All right. Go back, look at your notes, and see how we got that. Okay? All right. So, if you know the unit tangent vector, how does that relate to the unit normal vector? It is perpendicular, but three-dimensionally I can't look at that and tell you what's going to be perpendicular to it. So the next best thing is how theoretically does it relate to the unit normal vector? How do you get the unit normal vector? Yeah, you take the first derivative of that. So let's start there. Now, I'm not going to write it as a unit vector anymore because its derivative is not guaranteed to be a unit vector. So to keep from confusing you and thinking it is, I'm just going to write it as a vector, t prime. And that will be 1 over root 5 times what? Help me, somebody. Negative 2 cosine ti minus 2 sine t j, and that's all, folks. The coefficient of k is 1, the derivative of a constant is 0. So our derivative of the unit tangent vector is two-dimensional, which means, of course, that the unit normal vector is going to be two-dimensional. And since this is a lot simpler thing to fiddle with, it's also going to be easier to calculate the magnitude of that, because it's only two-dimensional. So what is the magnitude of that? Now, the magnitude of this unit, first derivative of the unit tangent vector, would be what? Right? excuse me, I've got a burp. Okay. It would be, when you square the first term, you get 4/5, because you got that 5 in there, cosine squared t, because the minus sign, plus 4/5 sine squared t, right? But you can factor out the 4/5, which would be 2/√5, right? And this is what Bill was doing, I think. And what you have left is the square root of cosine squared t plus sine squared t, which is 1. Okay? So that's the magnitude. So take this vector, so your unit normal vector, thank you very much, is going to be, oops, and this is a unit vector, so I can go back and put my hat over it, TP or whatever you want to call that, okay, is going to be the unit tangent vector from up there divided by this. Well, when you divide by 1/√5 by 2/√5, the root 5's go out, and you just have 1/2 square root, I'm sorry, not the square root, that's the, well, I can't get my eraser to come up. There we go. If I hit the right icon, it will. Okay? So this will be 1/2. But here we got 2's and 2's, so the 1/2 goes away. So basically what you have is minus cosine ti minus sine tj. You think that might be a unit vector? Of course it is, because cosine squared t plus sine squared t is 1. I mean, yeah, it's 1. Oops, leave it left off my parentheses. I don't really need it anymore, since I lost my 1/2. So that is your unit normal vector. Now I know I skipped a lot of steps there. Sorry about that. What we did was divide this thing by that thing, and that wiped out the 1/√5s. And that left us a 2 in the numerator here, but then you had, I'm sorry, you're dividing by this, so invert and multiply it, put that 2 in the denominator here, and then these two 2's that cancel that out, so you just have left minus cosine I minus sine j. That one was not bad to do because that worked out so nicely there. Okay. Does that follow, or is that too many skip steps? Okay. Now, is that pointing in the right direction? When you do it this way, I am almost certain that it guarantees to point you in the right direction. But if we needed to, we could check and see. Let's just take when t is equal to 0, that would be a 2i would be your displacement vector. 2 in the positive, okay, x direction. 0 for y and 0 for k. That's happened with any well, okay, this is a helix going like this. So to be pointing inward, when you're 2i outward, you point inward, a minus cosine t would be at t equals 0 would be a minus 1. So yeah, that is pointing us inside that helix. This is a helix, we knew that. So a minus cosine t, just where t is equal to 0, would be pointing to a minus 1. So that would be the displacement vector this way, the unit normal vector that way. So that makes sense toward the inside of that circle. Okay, I just chose that one. Theirs I don't think is drawn quite to scale, but it is always pointing to the inside of that circle. And these always point horizontally toward the z-axis. You're going up like this with the helix, but the unit normal vector is always pointing inside toward the z-axis in the plane perpendicular to z. Okay, because it has no z component. All right. I think you can trust the math to work for you on the unit 10 normal vectors. If you're doing the shortcut, you have to figure out which is the one pointing toward the inside when it's a two-dimensional. All right.
Go back a minute. When t is equal to 1,
Right.
you just have, is that a minus 1?
Okay. When t is equal to 1. Okay, cosine of 1 is positive. Okay. And sine of 1 is positive, and 1, of course, is positive. So your displacement. So you're up the curve somewhere here. That's 1 radian is about 57 or so degrees. So you're up here. 2 times cosine. This vector is like this, and the sine is, this one's decreasing, that one's increasing, and then t is just constantly going up 1. Okay. When you put a 1 in down here, you're opposite the okay. Okay. This is ugly writing. Okay. Here is your helix. T is equal to 1 is somewhere here. This vector, your R vector, is positive on X and positive on Y. Okay? And positive on Z. Okay? Your unit normal vector has to be pointing inward, and that's pointing this way, and that's toward the inside of the circle. So it has a minus I component and a minus J component. Is that what you're asking?
Yeah, well, let's try. See, at the bottom now, we got the unit normal down here.
Right.
Okay, just this unit normal vector right here.
Right.
Plug t is equal to 1 and there.
Right. So you get a negative I and a negative J. So you're pointing
just the opposite.
This is your x-axis.
Yeah.
So it's pointing toward and this is not got around to here yet. So you still, this vector is positive in x and positive in y. This is y-axis, positive x, positive y. First quadrant like that. So the unit normal vector, I should have been from this point, is pointing to the negative on x and negative on y to point towards the z-axis. It has to be in the opposite direction of that, but without the z component in it. So it's like that, kind of. And it always is like that, because it's always opposite direction. Kind of half the magnitude of that, of the xy part, but always in the opposite direction. So if your displacement vector is like this, this is in the same direction x and y, but it has no z component, whereas the r does have a z component. I can't get my fingers to work well enough to explain that. Okay. So that was example 4. Okay. Moving on then to tangential and normal components of acceleration. So we've been dealing with unit tangent vectors, unit normal vectors for whatever the curve is. The t didn't have to be time. Let's go back to the situation where we are now talking about motion, so t is time. And let me get that to go here. All right, there we are. Tangential and normal components of acceleration. Top of page 849. In general, part of the acceleration, the tangential component, acts in the line of motion, and part of it, the normal component, acts perpendicular to the line of motion. Okay? In other words, part of your acceleration could be either increasing or decreasing your speed if you are speeding up or slowing down. That's the tangential part. And part of it is in the normal component, which may be making you change direction. That would have to be tangential. Either tangential toward the center or away if you're going that way. Okay? And that acts perpendicular to the line of motion. So any motion you have, if you're in the straight line and acceleration is speeding you up or slowing you down, that's the tangential acceleration. But the other form, because acceleration is anything that changes the velocity, okay? And if your velocity is changing direction without changing speed, that's a normal component. And that is the part that changes, acts perpendicular to the line of motion, because it's either making you turn left or turn right and not go straight anymore. So that component is perpendicular to the line of motion. The tangential part is along the line of motion. The normal part is perpendicular to that. In order to determine those two components, you can use the unit tangent vector and the unit normal vector, which serve in much the same way as I and J do in representing the vectors in a plane. So if you have an acceleration vector, that always has a tangential component and a normal component. So rather than the xy axis, use those two and write the acceleration vector in terms of these two units. These are unit vectors, and these are perpendicular to each other, just like these two are. So that's what makes the connection there. Following theorem states that the acceleration vector lies in the plane determined by t and n. The unit tangent vector and the unit normal vector, the acceleration vector has to be in that plane. And here's the theorem that says it. The acceleration vector of r of t is the position vector for a smooth curve C, and n of t does exist, okay? Now, when would n of t, this is tough. When would n of t not exist? When your unit tangent vector is not changing. Unit tangent vector is the magnitude 1, but if it's not changing the direction, then then its t prime is 0. And the unit normal vector is t prime divided by the magnitude of t prime, which you can't divide by 0. So where n of t exists, anytime, like you said, it's changing direction. Okay? For a smooth curve C and n of t does exist, then the acceleration vector a of t has to lie in the plane determined by the unit tangent vector and the unit normal vector. The acceleration has to be in that plane. It's a vector also. Okay. May not be the same plane that the displacement vector is, but it has to be the same plane that the velocity vector is in, because that's in the same direction as this, and the acceleration would be in the same plane as that. Okay, the coefficients of the unit tangent vector and the unit normal vector in the proof of that theorem, now we didn't prove it, is it worth the time to take to prove it? because they are counting on that proof. Boy.
I believe it.
What's that?
I believe it.
Okay, you'll believe it, he said. The coefficients of the unit tangent vector and the unit normal vector in the proof of this are called the tangential and normal components of acceleration, and here's how they're defined. If you think about it too, just sort of in a cursory type sense, the tangential component of the acceleration, that is the component that's increasing or decreasing speed. Well, that's d by dt of your speed, right? The amount that is changing the speed of the object. That's it, right there. This is the speed that's changing the speed. Now, the normal component of your acceleration, that's in the direction of the unit normal vector, is that magnitude of your velocity vector, okay, times the magnitude of the first derivative of your unit tangent vector. Now that, to me, is maybe not quite as easy to see. Your unit tangent vector is this way. That's in the direction of the velocity. And your first derivative of this is how much that is changing, which means turning or not. And how much it's turning depends on the magnitude of that velocity. If it's turning just very slowly, but it's a very smooth velocity, it's not going to have a very strong normal component this way. If it's turning very rapid, if it's going at a high speed and changes just a little, it can have a pretty significant normal component. That's a lot of arm waving there, but then too, that's not nearly as obvious as this. So therefore, you can write your acceleration vector as a of t, this thing right here, times your unit tangent vector that's in the direction of motion, plus a sub n of t, which is this. Now notice that these are scalar quantities. These are components of the acceleration. The capital T's and N's here, and bolded there, said this is acceleration in that direction and in that direction. That's what those mean. But the A's themselves are scalars. And this is multiplied by the unit normal vector here. So this is a component of the tangent vector. The faster that is going, that's a large number. If it's just changing the speed very slowly, then that's a very small number. This one, if it's turning quite quickly, that's a large number. If it's turning very slowly, that is also a very small number. Okay? So this is one way to write that. Understand that is the definition of that. This is not an easy thing to calculate. This is not bad to calculate at all. This one can be a real pain in the neck, almost as bad as calculating the unit normal vector. Because you've got to take the derivative of your displacement vector, take its magnitude, and then take the derivative and then divide by its magnitude, and that gives you this, and then take the derivative of that, and then take the magnitude of that. So it's a multi-step process, and if you remember last time, it can get quite complicated. So this is not a user-friendly form. This one is pretty user-friendly. That's not bad. So part of our goal now is to come up with a simpler way to write that. Okay? And that's what the next theorem does. The following theorem lists some convenient formulas for a sub t and a sub n. A sub t wasn't bad to begin with. A sub n, pretty involved. There's a tangential and normal components of acceleration. R of t is the position vector for a smooth curve for which n of t does exist. Okay? Then the tangential And normal components of the acceleration are as follows. Okay? A sub t, like we said before, the first derivative of your velocity, the magnitude of your velocity vector or your speed function. Well, that's okay, but even easier than that is, well, sort of, perhaps easier than that, or on the same level is A dot t. Dot products are easy to do. It's easy to get the acceleration vector. That tangent vector, you have to get this to begin with, so why not use this one? But this isn't too bad either. Okay? But another way you can do is, since A is that in V over V prime. Hey, why mess with this to begin with? Okay? Take the derivative of your displacement vector, take its second derivative, dot product those two together, and divide by the magnitude of the first. So that's probably the simplest way to get there. It comes directly from here. Now, why they reverse the order of that, I don't know. If I were doing this, I would say A dot V dot over V bar, because that's exactly what T is. But this is pretty easy. Take the derivative of this, the second derivative of this, and take the magnitude of the first derivative. Okay. Now, A sub n, who is here? Okay, that's not bad. You had to do it here anyway. This is the pattern. I mean, you had to get this far, then you had to take the derivative of this, and then you had to take the magnitude of the derivative of this. Whew. Well, that's A dot n. And if you think about it, n has to be in the direction of V cos A. Right? Maybe it's not really obvious. The velocity is this way. Your acceleration vector is somewhere in that plane, so to speak, and the cross product is going to be toward the inside of that. So that's kind of making sense. Divide by this, and that's not so often. You just take these and this that you've already done, or rather than do a dot product, do a cross product, and then divide by the same thing you've already done. That's not too bad. But even easier than that, if you know this A, you can take its magnitude, right? And since the tangential component and the normal component have to be perpendicular to each other, take the magnitude of this minus this thing squared. Magnitude of this squared minus that thing squared has to give you the A dot n. Has to, because Pythagorean theorem. Acceleration vector here, tangential component of the acceleration vector there, the difference has to be in that direction. You know it's in the direction of your normal vector, so that's usually the easiest way. Once you've calculated this, square it. You've already calculated that, find its magnitude, square that, the difference in those, square root of that. A sub n. Now, A sub n, it says, note that is always greater than or equal to 0. Why? Square root, not a negative square root, principal square root. The normal component of the acceleration is also called the centripetal component of the acceleration. That's what pulling changing the direction, the acceleration is toward the center of the circle. Center seeking, centripetal. That's what that means. Center, and petal, I guess, means seeking, going that way. All right. So, with those tools under our belt, and by the way, this example 5 can be found at larsoncalculus.com, interactive version of this type of example. So, if this gets you confused, go there, and it may be able to clear up some stuff. Find the tangential and normal components of the acceleration for the position vector given by r of t is equal to 3ti minus tj plus t squared k. What you reckon your first step is? Take a derivative, always a good idea. R prime of t. For some reason my pen is not doing anything but sitting there. Okay, why are you doing that to me? Okay. This whole thing seemed to have frozen up here. Let's try. Microsoft PowerPoint is not responding. Let me try this first. Sometimes this will shake it. Let's first do that one and end that. See if this does anything. This is so irritating. I really don't like Microsoft products at all. Okay. Well, it's closing everything. Let's go back to this and back to here. 12.4. I think this is the one we just finished. So we'll go from current slide. Okay. There. All right. Like we said, we're going to do, oh, I've got to get my pen back. Okay. R prime of t. And that, by the way, is your v of t. Not that you need to know that, but yeah, it's helpful to know. What is this?
So
3i minus j
plus
2tk. All right. So that's helpful to know. Now, at some point we need to know something else about it. What would that be? The magnitude. So let's do that off here to the side. Magnitude of v of t is square root of, second, 9 plus 1 is 10 plus 4t squared. Agreed? Okay. So, there's that, when we need it. What else are we going to need to know?
acceleration.
Second,
Acceleration.
acceleration. A of t is the first derivative of v of t, which is the second derivative of r of t, which is 2k. There's your acceleration vector. Interesting, huh? All right. Now, what else are we going to need to know? Let's glance back to the past and see one thing we need to know. They're asking for the tangential and normal components of the acceleration. The tangential component of the acceleration is v dot a divided by v, magnitude of v. So I think we can do that. What is v dot a? I'm going to leave off my of t's here. Since they're right over each other, pretty easy to do. 3 times 0 is? 0, negative 1 times 0 is? And 2t times 2 is? 4t. There's your dot product. Okay? We've already calculated what v of t is. Magnitude of v of t is that. Right up there. So your a sub t, this is how they write it, your tangential component of the acceleration is the dot product 4t divided by the square root of 10 plus 4t squared. Okay, that's what it is for any value t. Okay. Yeah. All right. Now, the normal component of your acceleration. We could go back and do one of these other things, and that wouldn't be so awfully bad. But the easier way to do is take your acceleration vector, square it, minus the square of the thing we just did, and then take a square root of that. So your a sub n, oops, I like to do that with a hat on it, because that's a unit normal vector, is equal to the square root of a magnitude of a squared minus a sub t squared, right? Magnitude of a squared minus a sub t squared. All right. So, what is the magnitude of a? Should probably have done this here. Magnitude of a is equal to just 2 square root of 4. Yeah, there it is, right there. Okay? And since we just calculated a of t, if we squared that, what do we get? A sub t squared is 16t squared over 10 plus 4t squared. Now, there's not a lot you can do to make that much prettier. You could try a few things, but let's not mess with it too much. And let's just see what we've got here. It's the square root of, well, but now we're going to square that, so your 4 still works, okay? So that will be 4 minus 16t squared over 10 plus 4t squared. Pluses and fours are looking, or t's are looking an awful lot like each other, so don't get them confused. So you can write that a little bit better as the square root of 40 plus 16t squared minus 16t squared, right, over 10 plus 4t squared. What I did, I wrote 4 as 4 times this over that. Okay, and that enables the 16t squareds to disappear. Okay, and that leaves us to be (2√10) over the square root of 10 plus 4t squared. Okay. Now, we've done what they said. We found the tangential component, right here. And we found the normal component. That's it right there. Let me make sure I found it right, though. Oh, they did the cross product. Well, let's see what they got. 2√10 over, look at that, they got the same thing. I think our way was easier. I'm lazy, by the way.
Right below it, though, they did the other way.
What's that?
Right below it, though, they said you could do an alternate.
Right, oh yeah, and we did it that way, yeah. So, so we got this, yeah, we got the same answer both ways. And that's what they were looking for. Now, if you wanted to write that acceleration vector in terms of these, that would then be, and notice they have the same denominators, so that's what makes it attractive. your A, your acceleration vector as a function of t, is equal to 1 over the square root of 10 plus 4t squared. You can pull that out, times 4t times a sub t plus 2 root 10 times a sub n. Okay, and that's, for what it's worth, it's a fairly simple way to write it. Okay, frankly, I really don't see the advantage of this that much, but you could do it that way. It makes it look simple anyway. All right, they didn't ask for that, but you got it anyway. Too bad. All right, let's see how they did it. I think it'll be, like you were pointing out, very similar to what we did. They start with finding the velocity vector v of t, which is the first derivative of the displacement vector, which is 3I minus j plus 2t k, exactly what we got. Then they took its magnitude, which is the square root of 10 plus 4t squared, exactly what we got. Then they went back and took the derivative of it, a, which is r double prime of t, and that was just 2k, exactly what you got. Okay? Now, that in mind, you could go straight to a sub t, the tangential component, the component of the tangential, how do you say that? The tangential component of the acceleration, yeah, that's how we say it, is v dot a, which is simply 4t. They didn't show how they got it, but you know, if you did the 0, 0, and then 2 times 2t is 4t. Divided by that magnitude, which we just got, there it is. A sub t is usually pretty easy. Now, they then did the a sub n this way, which is okay, but it's just a little more work. You have to go back and cross these two, and they don't have them written down there, so it's ijk. I would do another ij here. 3 minus 1, 2t, 3 minus 1, and then 0, 0, 2, 0, 0, okay? And then when you did your work here, you get minus 2i, 0, 0, and then 0, 0, and minus I can't picture it now. Minus 2. No, it's not I, it'd be j. Yeah, minus j, okay. Without writing it out. Anyway, let's see what they got. Minus 2i minus 6j. Sorry about that. Because you had that 3 over there.
Oh, yeah.
Okay, sorry.
When I write it out, it makes it work.
It really does. Okay. I should have done that. Minus 6j. Okay? Now, what you have to do is take that thing and divide by this, which we already had, divided by square root of 10 plus 4t squared, which really wasn't too bad. Oh, wait. You have to find the magnitude of that. Magnitude of this is 40. Okay?
Well,
square root of 40. Okay? So this will be square root of 40 over this thing right here. Which is pretty much what we got. 2 root 10 over the square root of 10 plus 4t squared. So that wasn't hard to get either. And I don't think they did anything more. In fact, they end everything there without doing example 6 or 7. So how are we doing on time? We go till 2:55. Oh, wait. I can't do it. 155. 155. Getting everything out crossed up. So we got plenty of time to do both of these, I think. So let's back off here. Ooh. Let's see if I can get more white space here. I think I can. Yeah. So let's do that. Any questions? I should have asked questions before I removed the other. Were there any? All right. Example 6. Find a sub t and a sub n again for a circular helix. Okay, find the tangential and normal components of the acceleration for the helix given by r of t is equal to b, oh, no numbers here, cosine t I, whoops, yeah, well, it helps if I write in the cosine. Cosine t I plus b sine t j plus ctk. Now what makes that a circular helix? Yeah, the b's are the same. Yeah, if one of these had been an A and one a B, B and C or something that are different from each other, it would have been an ellipse. This with the same, that's going to be circular. And what makes it a helix is the fact that you're going up by t, some factor of t. Okay. Not a single number in the problem. Okay. Now, find the tangential and normal components of the acceleration for the helix given by that. So what might we do first? Okay, take a derivative. R prime of t, which by the way is your v of t, is equal to negative b. Stop, you got me saying it, yeah. I shouldn't listen to you. Okay. Minus sine t I
plus b
cosine t j
plus
ck. All right. Now, what might we want to do while we're here?
What you do with 2k here? On the end, doing the root of t squared to k, right?
Oh, wait, that was the previous problem.
Oh.
Yeah, they don't have this one. This is the new problem. Yeah.
Oh, my bad.
No, no problem. I shouldn't really use these again, but, or if I do, I should do this. Okay. All right. Magnitude of v of t. I'm just going to leave it v so I don't have to write as much. Can I just pull out the b to begin with? Otherwise, they're going to square it into the thing. And then what would that give us? It'd be square root of 1, which is 1. Oh, wait, no, I'm sorry. I forgot about my c there. I mean my k component. It's the square root of 1 plus c squared. Is that right? Yeah. Okay. I was jumping ahead to the next one, but too early for that. Okay, the b, no, the b can't come out. This is b squared. Sorry. Because that c is still in there, I can't do that. Okay, sorry. I was trying to be, too lazy. Okay. Oops. There we go. I think that's right now, right? Square root of b squared plus c squared. Because the first two give you a b squared. The second one gives you a c squared. Okay. Now, let's go on to the next step. R double prime of t, which is v prime of t, which is a of t, is The C derivative of that is 0. Okay, find the tangential and normal components of that helix. All right. Now, having written them over each other like this, your tangential component, A, well, let's not write it as a vector. A sub t is what? Okay, V dot A. So let's do that right here. And what do we have? B squared times sine squared plus cosine, what? Sine cosine. Right? Okay. Minus B squared sine squared cosine squared. What's that?
Well, they're squared.
What's that?
Are they squared?
Didn't I?
Oh, yeah.
I multiplied these two together. Oh, I'm sorry. I keep wanting to do that. They're not squared, no. That makes it worse. This makes it easy. What do those add to? 0, exactly. So your tangential component of your acceleration is 0, which means it's not speeding up. Not speeding up. The speed's the same. It's
not turning.
Yeah, it's in a circle. You're doing centripetal acceleration only. So there is no tangential acceleration. It's all centripetal, all pulling it toward the center.
Would we have known that
when we said it's a circular helix? That basically tells you that. There is a z component of the velocity, but you lose it here. Hey, good to see you. If I can find my pen. Oh, there it is. Corey's here. All right. Now, I've been meaning to ask this since the last time you were here. They told me that you sometimes left because you had such a long way to go home. Would it help if we moved the classes closer to each other in time? What's that? Yeah. Okay. Now I can do that easily on Mondays. Wednesdays, I usually count. The break between this is when I finish my lunch. So I can wait and finish the lunch on Monday, because that's no problem. I have from 3:45 to 6 open. But on Wednesday, I've got to book it to the other campus. So what I can do, if I can get my salad and sandwich eaten in time, then I can eat my fruit when I'm going over there. So I think we can do it both days. So, yeah.
We would probably just take a break. Almost still the same break,
but just a very short break, like 5 minutes, rather than 35 minutes or something like that. Is that okay?
Yeah.
Okay. Is that all right with y'all? I know you usually eat lunch. Huh?
I'll just bring my lunch in here.
Okay. That'll be fine. Okay. And if 5 minutes won't work, we'll stretch it to 5.5. No, 10, 15, yeah, I mean, whatever. But we won't do a full 35 minutes. Okay. Is that all right? Bill, you okay with it too? Mr. Stokes, are you okay with that too?
I'm okay with whatever they do.
Okay. All right. We'll do that today then too. I'll just take I've got to go down and swap books, so it'll give you all time to potty call or whatever you need to do. Okay. All right. So we just found out that the tangential component of the acceleration is 0, meaning it's not speeding up. That's what that means. The speed is not increasing. It is accelerating, but it's always toward the center. In other words, it's centripetal acceleration. Well, that's what makes it circular. A circle has no change of velocity. It only has a change of direction. Circular motion. Okay. So, this confirmed it. Now, that means, oh, what was the next step to do anyway? Why did I jump the gun? Oh, yeah. I hadn't finished doing this, but this is 0. What would have been, oh no, there it is. That's what I need. So what we have now is a sub n, the normal component of that. Since the tangential component is 0, it's just this right here, minus b cosine t I minus b sine. Well, wait. This is a vector. We don't want it being a vector. It's the square root of the magnitude, right? Of the magnitude squared, right? It's, well, let's write it here. It would have been the square root of a squared minus a sub t squared. Well, all it is then is the square root of this is 0, so the square of that is that. So it's just simply the magnitude of the acceleration vector. Right? Because the square root of a square is that. So what is the acceleration vector? It's a square root. And what is it, the square root of it?
It's b squared.
B squared. This one is the one I wanted to pull out the b, and then what you got left is 1. Okay. So that's what I was trying to do before, but I dropped the gun and was doing it on the wrong one. Okay. It's just b. So, believe it or not, this acceleration vector is b times a sub n. No, a sub n is, it's a, yeah, b, I'm sorry, b times, I keep getting this, okay, b times your normal vector, okay? Your, not normal, yeah, your normal vector, unit normal vector. Because there is no tangential component, it's just that. And if you go back to, let's see how far we have to go back to see it.
Okay, do me a favor.
What's that?
Do me a favor.
Okay.
Make some physical sense out of this.
Okay. Let me, hold on just a minute, and let me just take this back. Here, your acceleration vector is your tangential component times the unit tangent vector plus the normal component times the unit normal vector, and the tangential component was 0, so that's why I said it was just b times the unit normal vector. Okay, now, that's what I have there. Okay, now.
Okay, I'm coming this way now.
Okay.
Okay.
Here.
At some point I'm going to try to turn.
No, you're turning constantly. You're in the circular
Okay,
helix.
this is the helix now.
Yeah, circular helix. That's what this is, circular helix. That means I'm never speeding up at all. At all. Oh, wait. Well,
Because of the velocities.
yeah, my speed is this, yeah. It's a little bit, it is speeding up. But in the tangential direction, it's not speeding up at all. That's what this told you. The only acceleration is toward the center. That's what makes circular motion. So you've got some climbing going on here because your velocity vector does have a component here. But this component is constant, and that's constant, so that's why this is no t dependence on the velocity at all. Okay, your speed is a constant square root of v squared plus c squared from that. Okay, but your tangential component, the acceleration in that, see, again, this is constant. There's no t here. So if there's no t on your velocity, then it's derivative. And if you go back actually to an earlier definition, remember this one? A sub t is equal to where was it? Yeah. I turned the pages already. Here it is equal to the simple one. Yeah, that's it. Yeah, is d by dt of the magnitude of v. Okay? Your tangential component of the acceleration vector is the first derivative of the speed. This tells you the speed is constant. So the first derivative is 0. So that would have been an even easier way to get here than doing the dot product. Dot product was easy, but we could have gone back to that and said, hey, that's a constant. First derivative is 0. So you have a constant speed in your a constant speed, period. Okay, the constant speed as you go around that helix. Acceleration is not constant because it's pulling you inward, but because the tangential component is 0. Okay, the acceleration vector, the tangential component of the acceleration vector is 0. All of the acceleration is toward the interior. Okay, and your acceleration is, this is 0. Here's your acceleration minus v this. So you do the magnitude of this right here, and you get v squared cosine squared plus v squared sine squared. Factor out of v squared, you get 1, and square root of v squared is b. So that's why this turns out to be. So your acceleration is a constant pulling you in toward the center of the circle, and that's what makes circular motion. Now, if you go back to physics, I don't know if you are interested in doing physics at all, that B is your centripetal acceleration, which we usually use that symbol for, is v squared over r. Okay. Now, of course, you could play around with this some and see what that gave you. And I think, well, let's not get into that. Okay. That mixing up two separate ways of using the symbols. Huh?
Isn't R usually time?
R is usually what?
Time?
R is not time. R is your displacement. But it's the magnitude of R. So it's the radius. Wait, I'm sorry, that's completely different. That's the radius of the circle. And the radius of the circle is B. It's C, I think, isn't it? I don't know. That's a different R. That's why I said it's mixing up the symbols. So let's not do that. But that's what's going on here. You're going in circular motion here, so this tells you your velocity is constant, not changing, no time dependence on it. And with that happening, that was another way to see that the tangential component of the acceleration was zero, because you're not speeding up any. So all of your acceleration, that you know is right here, this acceleration is normal. And so since that's zero, you just figure out what the magnitude of this is. That's b. Okay. Square root of b squared cosine squared plus b squared sine squared, and factor out sine squared plus cosine squared of b squared. Square root of b squared is b. So that is your total acceleration. That's the normal component. Everything is pulling you inward, and that's what makes it centrifugal motion all the way.
I'm asking some more questions.
Okay.
Don't take it out on me.
No.
Is there any way that the tangential portion can be zero?
Tangential?
Yeah.
The tangential acceleration is zero, so the tangential force is zero.
Okay.
Yeah.
That'll answer that.
Because you have nothing speeding it up or slowing it down. It's going at a constant speed, so its tangential force is zero.
Suppose the velocity vector is slowing down. This thing is going to grind to a halt, just stop, right?
Okay, yeah, it's going to spiral inward and ultimately crash. It's
Okay,
the- yeah.
okay, that makes some sense.
Yeah.
At least I learned something while it crashed.
Yeah, right. And that's what, remember we had a space station up before we had the International Space Station. The U.S. had one up, and the Russians had one up. Was theirs called Soyuz or something like that? And ours, we couldn't keep it in orbit, and it spiraled down and crashed. I think we had pretty much used it up anyway, but theirs stayed up a bit longer. We used it for a while and replenished it using our shuttle fleet. That's when we got to doing the most together. When ours crashed, we worked with them, and it worked pretty well. So that led to the International Space Station, which was then truly international, and it's been doing pretty well since. But that's politics, okay. All right. By the way, I didn't say this when you came in, should have, Corey. We're in Chapter 12, vector-valued functions, and 12.4 is tangent vectors and normal vectors. That's what we've been talking about here. We're on page 851. We just finished example 6. We're getting ready to start example 7. Except now that I've talked so much, we may not finish this one. Let's see what we can do on it, though. We've got about less than 10 minutes, don't we? Okay. Again, new problem here. The position vector for the projectile shown in figure 1227 is r of t is equal to 50 root 2t I don't like writing it that way, but that's how the book is writing it. I plus 50 root 2 t minus 16t squared j. Two-dimensional, planar, okay? Says find the tangential components of acceleration when t is equal to 0, 1, and 25 root 2 over 16, one of my favorite numbers in all time, okay? So we want a sub t as a function of t when t is equal to 0, 1, and 25 root 2 over 16. Okay. So, where do we begin? Take a derivative. R prime of t, which is also your v of t, is equal to what? Pretty easy. 50 root 2 in the I direction plus 50 root 2 minus 32t in the j direction. Okay? Now, while we're there, I'm going to go and take the magnitude of that v. Anyone got an idea what the magnitude of that v would be? Okay, 50 root 2 squared would be 2,500 times 2, which would be 5,000, right? Is that the first part? Okay. Plus, now when you square this thing, you're going to have that same 5,000, right? Minus 2 times the product of those two things, which is an awful looking thing. That would be 3,200 root 2 t. Am I right there? Because twice the product. Twice 50 is 100. Times 32 is 3,200 times root 2 t, plus this thing squared. That's awful, isn't it? 1,024? 32 squared? You got a calculator? I'm guessing. I'm not at all sure on that. Or 1,040 maybe? No.
1,024.
1,024?
Yes.
Okay. I did guess right. Okay. Now, that's what you get when you square that. So, let me just make that 10,000 when I add the two 5,000s together. Is that okay? Just because I'm saving room. 10,000. That's pretty ugly. Save room for ugliness. Okay. It's one of my mottos. Okay. 10,000. Let me, oh yeah, go on and, oh, I forgot my t squared here. Okay. And that's going to be a minus 3,200 root 2 t plus 1024 t squared. Why did I ever want to do this? Okay. Since we're doing this just at 3 particular times, do we have to do it for all time, or can we go on and plug in? Since we've gone this far, let's leave that alone and go on to the next step. What else next might we do? our double prime, how are we doing on time? We're running out, aren't we? Our double prime of t, which is v prime of t, which is a of t. What's that?
This one I can handle. It's negative 32.
Negative 32j. Right? All right. I think that's going to make a lot easier. Right? Okay. I think that's all we need in order to trying to remember back the shortcut. Remember our shortcut when you're in two space? Yuck. One of the first things we did. Yeah. It's only after you got in your unit. Yeah, sorry. That was a different issue. All right. So I think that's all we need. So your A sub t is equal to what? V dot A, remember? Okay. The V part, the I part goes to 0. And the J part, when you dot those two together, you get okay. These cheats, okay. But when you dot those two together, the I goes to 0 and you get that. And what this is negative 1600, isn't it? Plus 32 squared t. Okay, and then you divide this by your r prime, your v prime, which was this awful looking thing here, the square root of 10,000 minus 3,200 root 2 t plus. And here's what they do. They list that as 16 squared. How did I get 32 squared? They got 16 squared. I must have really botched something up there at the very beginning. Oh, I see what they did. They pulled out a 2. Okay, got it. No, so we're not going to have time to finish, obviously. Ooh, especially if I keep erasing everything. Okay, I'm just going to leave that 32 squared t squared. Okay. We're running out. In fact, we've run out of time. We basically were right at the point of being able to, in fact, they factored out a 32 in the numerator and a square root of 4 in the denominator, which so it made their whole life a lot easier. And then they did some approximations. I mean, they just plugged in.
Kind of half did the math.
Yeah.
Did it at the end.
Well, yeah, you do that, but then you plug in t is equal to 0. That makes a lot of things simple. And then you do t equal 1, and that makes a lot of things simple. And then that last one, which looked like a real big pain in the neck, you get to cancel a lot of things out, and you wind up the tangential component with 0. And what happens there, it means that's where it's reached its maximum, and it's going down, because this is a parabolic shape. And if you recognize the form from physics, this is your initial velocity, there's your acceleration. So that's all this is a big parabola. And when you reach that time over there, you reach the peak, and that's when it starts coming down. So that's what they're showing here, but they didn't tell you that's what they're showing. But this is parabolic two-dimensional motion. What do they call that? Projectile motion. They call it free fall. Various names, and that's exactly what it is. It's just they gave you huge numbers to play with. But as soon as you get to this form, then plug in a 0. Things will come up so much easier. And as you see, when you plug in a 0, this term right here becomes 100. Square root of 10,000 is 100. And this thing up here becomes 16 minus 1600. So there, your acceleration is minus 16. Yeah. So whatever. So that's where they're going with it. Unless y'all want to come back and do this, can you follow it through at home, or you okay? You want to come back and wrap this up next time? Which, yes, wrap it up next time? Okay. Let's do that. We'll try to pick up where we left off today if I can remember. But homework exercises here include any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat. 9's at Calc View. 15 to 19, they're all at Calc Chat. 15's at Calc View. 21 or 23 are both at Calc Chat. 25 to 29 are all at Calc Chat. 27's at Calc View. 31 or 33 are at Calc Chat. 35 to 39 are at Calc Chat. 35's at Calc View. 41 is just sort of a just talking. Think through that and explore it. 41 Calc Chat. 43 should be at Calc Chat. 45 should be at Calc Chat. Any of the odds 47 to 51 should be at Calc Chat. 53 or 55 should be at Calc Chat. 57 or 59 should be, no, I'd say 57, any of the odds 57 through 63 should be at Calc Chat. 65 or 67 should be at Calc Chat. And then there's a true false, 69 should be at Calc Chat. And then 71s should be at Calc Chat. 73 and 75 are proofs. So one of them looks like one we've already done, but you can do that. So we will end with example 7. Go back and try to wrap that up, and then go on to 12.5, which I think is the last section in the chapter. Yeah. So when we finish 12.5, I'll be giving you your test. In fact, I'll try to have your test ready for you next time, and that way you can work on it, have an extra weekend to work on it. Okay?